gentlemen and lady. It's Friday 11:30. We're here at the group exhibit Hydrogen Fuel Cell and Batteries on the Hanover Fair. We're following here interesting discussions after each presentation. So if you're welcome to post a question after the presentation. So if you wake up and look at your notes after the presentation, then you can post some question. Now we see non-flowing through air-independent fuel cells for advanced aerospace applications from Mr. William Smith, President of Infinity Fuel Cells and Hydrogen. Welcome.
Thank you. Thank you. Well, thank you very much for this opportunity to tell you a little bit about our company and air-independent fuel cells. At Infinity, our primary markets are for space, undersea, and remote energy storage. And we've been developing these technologies for about the past 10 years. And the special thing about what we've been working on, as the title of the presentation says, we've been working on air-independent fuel cells, meaning pure hydrogen and oxygen fuel cells that go where there is no air. And one of the special things about that is we're using what's called a non-flow-through technology. I mean, most conventional proton exchange membrane fuel cells remove the water by entrainment or evaporation. But we're doing a different technology that removes it directly in each cell, but it's not actually a brand new technology. It was originally developed for the Gemini fuel cell program a long time ago in the 1960s. And that was actually the first practical use of fuel cells. And this passive water removal technology was demonstrated in prior NASA programs, and what we're doing right now is that we're advancing the technology using materials and systems that are available today that were not available almost 50 years ago. And for those of you that where Nafion is near and dear to your heart, this year marks the 50th anniversary of the use of Nafion in fuel cell systems. In 1964, the first program was started, again, a NASA program by General Electric for a fuel cell for a program called Biosatellite. Now, the Gemini system design was successful, and one of the main reasons why it was successful was this non-flow-through technology allowed the systems to be very simple. So you didn't have to circulate oxygen or circulate hydrogen. You could just simply bring in those two reactants and have a very clean, simple integration of the system. And this flew in 1965, so the years are getting on now for fuel cell technology. Now, our focus, again, has been military and NASA programs, and those are very demanding requirements. First of all, we have to use pure hydrogen and oxygen. It has to have very high efficiency and long life. We're designing for 10,000 or 20,000 hours of operating life, and unlike most of the other fuel cells here, we can't rely on gravity. It has to be a zero gravity system, has to be free of any power conversion. The fuel cell itself has to be able to operate within a regulated band, and of course, because you have to launch it, it has to be lightweight, compact, and you have to have little or no venting of reactants, so you can't purge on a routine basis because you have to keep everything that you have. And probably different than most fuel cells, you have to have gas-free potable water come out of it because your astronauts are going to drink that, or you're going to use it again in a regenerative fuel cell reaction. And you also have to do all of this while withstanding launch shock and vibrations. Now, what is it that I'm talking about when I talk about a proton or a passive water removal non-flow-through technology? Now, this is what we're doing. As water forms in pure droplets at the cathode, typically it has been removed by evaporation or entrainment, like I said before, but what we're doing is direct passive water removal using a pressure differential. So what we do as the water forms on the surface of the gas diffusion layer, we have a structure right nearby, a hydrophilic porous plate that touches that droplet, and then the droplet transports across that porous plate. Now, what's unique about that porous plate is that it allows water to go right through it. So it's a very effective water removal system. However, it does not allow the oxygen or the gas to go through it, so that it allows you to do separation of gas and water within each cell, which is a big deal if you're in space. because in space, of course, there is no up and down, so you have to do some form of phase separation. And traditionally in space, that's done using rotary separators, which are unreliable, complex, and consume power. So this is a very attractive way to manage your fuel cell product water in space. And what's the benefit of doing this? Well, the primary benefit is the elimination of ancillary systems. So where you have systems that have to circulate gases, as what's shown on the left-hand side of this slide is an alkaline space system. This is the kind of system that's used in the Space Shuttle Orbiter. And there you have to circulate the hydrogen because you get mixtures of water and hydrogen. And you have pumps and phase separators there. If you project to use an active proton exchange membrane system in space, you have to worry about separating the product water and oxygen on one side, and then water that may condense on the hydrogen side. So you end up with two sets of separators and pumps. But in our system, you can eliminate all of them. And the benefit of doing that is considerable, because if you're NASA, you can't afford to have one system. So typically on the Space Shuttle, for instance, they have 3 fuel cell systems, and all 3 of them have to be functioning. That means all 3 systems have to have their parasitic loads running at the same time. And so you can see that we projected some efficiencies as compared to the Space Shuttle Orbiter, and you can get considerable efficiencies, especially at low power, where the parasitics are a higher percentage of the total, and you get also very good efficiencies at higher power as well. They're not flying the Space Shuttle Orbiter right now, but this projects to future space systems as well. So based on what we have done with NASA in the past, and when I say we had some extremely talented, experienced members of the team, Al Meyer and Jim McElroy, who, if you're around the fuel cell industry, you know them, that worked on the Gemini program, that actually worked on the Apollo program. And we brought that kind of experience to bear, along with new technologies, to develop a new class of fuel cells for NASA and now for other applications as well. And some of our major accomplishments. So we started out doing this technology in 2006 with an SBIR Phase 1 program from NASA Glenn Research Center. And we evolved that over the past number of years through large format cells, and then up to recently in 2013 and 2014, successful testing of full-scale cell stacks that operate in many kilowatts and at high voltage. So it's in a relatively short time in the fuel cell world, we've taken it from a little concept idea all the way up to successful cell stacks, especially with the assistance of many in the industry and many in this room as well. So what this has led to is that we've been selected by NASA as their preferred next generation fuel cell for whatever missions are coming up. We were originally scheduled to be on the what was called at the time the Altair Lunar Lander, which was part of our NASA's space station or space constellation program, it was called, and our fuel cell would have been the fuel cell to power that. However, that lander was canceled. Fortunately, NASA kept going with the technology, so we've been able to keep bringing it forward. Now, as an air-independent fuel cell, it naturally has application for undersea uses as well. And that's what we've been doing. We've been developing, with the Navy's help, a series of these fuel cells for unmanned underwater vehicles. And the benefits there are, in addition to being very simple, the Navy also cares that it's rugged, because these systems eventually have to be able to survive a Navy environment, and that means possibly surviving depth charge attacks nearby and surviving. Again, not a typical requirement for your average stationary fuel cell. It has to operate at high voltage. The requirements there for the Navy are in the range of 240 to 320 volts. And of course, be simple, quiet, reliable, high efficiency, and small and light as well. And near zero venting, in this case for the Navy, means something different. It's not just conserving reactants, it means it's less detectable. Now, as we developed this technology, we didn't want to sacrifice performance you normally get out of a fuel cell. And what we've been able to demonstrate is that the technology is able to respond very rapidly to loads, and it, even as a passive system, as an on-demand system, It's able to operate at very low current densities for long periods of time, and then immediately jump up to high current densities when the load demands, and then drop right back down again. You know, all of this without having any pumps, fans, blowers, or anything else. And it also, in the process, we've been able to maintain high performance out of this system. Now, these are cells that are designed to be long life cells. So, if, again, any of you familiar with the fuel cell industry, means you're probably not going to choose a 1 or 2 mil thick membrane, a thin membrane for that. So we're using membranes that are tough catalyst formulations that are designed for long life, and yet we still maintain excellent performance out of these cells. Now, interestingly, the technology that we've developed, which is a all-metal diffusion bonded cell technology, is extremely strong, extremely robust. And in fact, if you see our fuel cells look round, most fuel cells you see are square. And the reason for that is that the same technology we've adapted to be able to operate as a high-pressure electrolyzer. And so the high-strength circular all-bonded cells we've adapted to develop a family of high-pressure electrolysis cell stacks. And we've employed some of these in an interesting program that we've had with the US Navy at the Naval Air Warfare Center in China Lake, California, which is about 40 miles to the west of Death Valley. They have a problem there where they have a flying range, a very large flying range about the size of our state of Rhode Island, and they have power systems distributed around it, and they're looking at different ways to power that. And what we did there is we developed a high-pressure regenerative fuel cell system, and that entailed developing our own 5-kilowatt solar-powered trailer. This is fully automated, self-deploys, along with a 5-kilowatt and 30 to 50 kilowatt-hour regenerative fuel cell trailer, which has inside of it a 2,000 psi high-pressure electrolyzer, again derived from the non-flow-through fuel cell technology. Now, this may be of some interest in the future to the military as well as terrestrial applications. So what we're doing is, if you look at our technology, we've met demanding NASA requirements. We have a rugged design that supports Navy needs and military needs in general. That trailer system was designed to fit on C-17s and be shipped anywhere in the world. We have additional undersea and aerospace applications as a possibility. The Navy isn't the only one that cares about air-independent systems that have to go underwater. There's plenty of oil companies out there looking around deep under the sea, and sometimes they have more money than the Navy. The same bonded cell design has translated to a family of high-pressure electrolyzers for the military applications. These may also have application for civilian use as well in being able to store renewable energy. So in general, what we're doing is building from this base of technologies that we develop for non-flow-through air-independent fuel cells for NASA work and electrolyzers to the military. We're bringing that down to earth now to serve civilian needs. Okay, thank you.
Very fine, and thank you very much. So this is a very astronautic theme. For me, it was a kind of overview for a really vast future, and that we can move right now with your technology. Are there questions allowed from your side with the audience together? So, did you take your notes in mind? Is there any question for this theme right now?
No.
Ah, okay. They're still thinking, I see. So, if there arise some question lately, it's at booth D77.
Yes.
Yeah. So you can meet him directly, and you can take the questions that belongs to the president directly. Yes. So really deep going into the theme. I have to thank you, Mr. William Smith.
Thank you.
See you soon.
See you.
And this was Now Floating Through Air-Independent Fuel Cells for Advanced Aerospace Applications by William Smith, President of Infinity Fuel Cells and Hydrogen.
Okay. Thank you very much.
As next, in 15 minutes, starting at 12, the low price in SMER until PMFCS, Stacks Testing Stations, Valdemar Stelita, CEO and Marketing Manager, Novel Cells Energy System SA.